Alright, hello everyone. The topic for this lecture is cross-site request forgery, or in short CSRF. Similarly to cross-site leaks, this is also a client-side web application vulnerability, meaning that we cannot use it to compromise the server. However, what we can do is we can force a user's browser to perform unintended actions inside the vulnerable website. To illustrate this, let's take a look at a very simple example of a CSRF vulnerability. Let's say we have a website where users can log in, and after logging in, there is a logout link which can be used to log out. And if you look at this link, we can see that it performs a GET request, sending the parameter action equals logout. Now, this should indeed work, but the problem here is that it is trivial for an attacker to force a user's browser to perform this action against the user's will. For instance, the user will get logged out from the website when clicking on such a tiny URL link received from the attacker. Why? Because when opening the link, the user's browser will be redirected to this URL, which will log out the user from the website. Or alternatively, the user will get logged out when visiting the attacker.com website, which contains somewhere hidden this type of an image tag. Now, this URL actually does not point to an image, but the browser doesn't know it. Hence, the user's browser will try to download the image by sending this HTTP GET request along with the user session cookies, leading to the user being logged out from the website. And just to note, this image tag exploit is actually much more stealthy because the request will be performed in the background. Whereas in this case, the user's browser will be navigated to the target website. But anyhow, as you see, this is not a nice situation where by visiting attacker.com, user gets automatically logged out from the affected website. Logging out, of course, is not the worst thing that can happen, but I think you got the point that this is a problem. So in essence, CSRF enables forcing the user's browser to perform unintended actions in the target website. Note that the attack is blind. Due to the same origin policy, the attacker cannot see the returned response to the victim's browser. But this should not be the problem in practice, and we can even use it to perform a multi-step CSRF, for instance by using JavaScript to introduce a delay between a sequence of forged requests. But let's think about why is this attack possible. Now, the first reason why this attack is possible is because an attacker can predict the request parameters. For instance, if this request here contains some secret value unique to the user, the attacker would not have been able to perform this attack. Another important reason why this attack works is because session cookies are included in cross-site requests, meaning requests initiated from other websites. But this behavior is actually inherent in how the web works and how it has been designed. Now, here you may ask, is this indeed always needed? For instance, why the heck would you need to include session cookies here when making a request to download an image? And indeed, in most cases of cross-site requests, this is not needed, but we will discuss this more on a later slide. And just to be clear, converting the GET request to a POST request here does not help us, at least on its own, because as we discussed in the previous lectures, it is also possible to perform cross-site POST requests using the HTML form submission or the Fetch API. So to exploit a POST-based CSRF, the attacker would have to set up a website, for example at attacker.com, with the following HTML code inside it. So when the attacker's website would be opened, the POST request would get automatically submitted to the vulnerable website. This will not be too stealthy attack as the victim's browser will end up in the target website. A more stealthy attack can be executed by performing the HTML form auto-submission inside a hidden iframe. So this code would be put inside an iframe, and the result would be that the hidden iframe would get redirected instead of the entire window of the attacker's website. Or another stealthy method is to submit the POST request using the JavaScript Fetch API as we discussed in the previous lecture. So, in principle, from the attacker's perspective, it does not matter much whether the vulnerable request is a GET or POST request. However, we indeed should convert these type of requests to POST requests. And here is why. So let's discuss the GET versus POST requests again. We already discussed that sensitive data should be transmitted in a post request body, as the data in a URL can leak in various ways. However, there is also another very important principle that should be followed in web application development, namely that a GET request should not alter the state of the website. It should be idempotent, or in other words, it should perform a read-only operation, meaning that it should be safe for a browser to send any type of GET request or visit any URL, perhaps even repeatedly, without causing any harmful side effect to the website. Now, but why would it be useful to follow this principle? First of all, this enables a safe sharing and bookmarking of links without causing unintended consequences like performing a transaction or altering data. Imagine that we bookmarked the URL that triggered a deletion every time it was accessed. This would have serious consequences. Also, GET requests are often cached by browsers and proxies for performance optimization. If GET requests are allowed to modify the state, it would lead to unintended result when the request is served from a cache. Then it enables web crawlers to safely crawl links, as it would be very bad if crawling a link would perform some actions, such as making some reservations in the website or other types of unintended commitments. Now, if this principle in website development is followed, then CSRF protection is required only for post requests, as performing cross-site GET requests by definition should be harmless, right? Hence, if we follow this principle, we can focus on CSRF protection only for post requests. As you will see later, this principle is also presumed by some of the CSRF protection mechanisms. Here, however, it is important to emphasize that it is crucial to prevent HTTP method mixing and override. The attacker should not be able to convert a post request to a GET request such that it is accepted by the server. Therefore, it is important to write code that enforces the correct HTTP method for a request. Here is an example of bad code in PHP, which performs input parameter lookup using both post and GET methods. In PHP, this request array contains parameters from both the GET and POST methods, and actually even from the cookie input mechanism. So if this is how a web application looks up the input parameters, then it enables converting a POST-based CSRF to a GET-based CSRF. This not only enables an easier exploitation, as then the entire request can be embedded in a URL, but also may enable the CSRF vulnerability in the first place in case anti-CSRF measures are applied only to the post requests. Another issue to watch out for is that some web application development frameworks may support HTTP method override. For example, by specifying the method parameter in HTML forms, which will force the application to interpret it as a GET request rather than a POST parameter. Some frameworks may support an HTTP request header for overriding the HTTP method. This cannot be used in a CSRF attack, as the attacker cannot force a user's browser to make requests with a specific header. But this could be used in another attacks where the attacker would bypass validation and send requests using HTTP methods forbidden by the server. But alright, let's take a look at some CSRF exploitation examples and the potential impact that this vulnerability can cause. As mentioned before, CSRF could be used for performing unintended actions and transactions on behalf of a logged-in user. For instance, it would be very terrible if there was an online bank where payments could be performed just by executing such an unprotected request, which requires only to specify the recipient and the amount to be transferred. Changing account settings, such as the user's email address or password, is also a very popular attack target, because if the attacker can succeed changing the user's password, then the attacker can log into the user's account, which obviously provides more capabilities to the attacker than what can be done using a CSRF attack alone. This is one of the reasons why password change forms should also require input of the current password. Adding email redirect in web mail is another interesting exploitation scenario. Here, the idea is that a victim opens a phishing email in a vulnerable webmail application, clicks on a CSRF exploit link, and later, if the victim is lucky, the victim may notice that under the webmail settings, there is added an email forwarding to the attacker's email address, which was added as the result of a successful CSRF attack. Years ago, there was one very popular open source webmail application that was vulnerable to this type of attack. And at that time, this was a very popular method of how to compromise a victim's email account. It was also reported that a similar type of exploit was used to compromise a small number of accounts of the Estonian email provider mail.ee. Here is a screenshot where you can see that some unauthorized email addresses have been set up for email forwarding. Another frequently overlooked exploitation scenario is logging a victim into the attacker's account on the target website. This could be the case if there is a CSRF vulnerability in login forms. It is quite common to overlook that CSRF protection is required also for actions that are performed by unauthenticated users, and this can also bring harmful results to the user. For instance, framing someone by forging submission of illegal information is an exploitation scenario that could also affect unauthenticated users. Consider publicly accessible feedback forms that are not protected against CSRF. In such case, an attacker could force the victim's browser to submit some death threats, bomb threats, or even to upload some illegal content if the file upload functionality is provided by the vulnerable form. Similarly, news websites where comments can be posted under articles could also be exploited to force the victim's browser to post, for example, hate speech or any other information for which the victim might be held liable. Now, the problem here is that these requests will be made by the victim's browser and will come from the victim's IP address. Therefore, these actions would be traced back to the victim, and the police would then knock on the doors of the victim. As you will see later, if the web server keeps detailed enough logs, it might be actually possible to prove that this was a cross-site request forgery attack. But at least initially, such an attack may mislead the investigation. Spoofing embarrassing search history is a similar attack, where the attacker's website opens a window to Google with a preset search query. The problem here is that even though the user did not enter this search string, this search will be stored in the user's browser history, and also the Google search history, which under some circumstances could be accessed by law enforcement authorities. And this type of framing attack is actually quite feasible in practice. So these were some of the possible CSRF exploitation examples to mention, but let's now move on and discuss how we can prevent CSRF attacks. The recommended and the most reliable method to prevent CSRF attacks is the use of CSRF tokens. The idea here is that there is a unique, secret, and unpredictable value that is bound to the user session. We call it a CSRF token or nonce. And this token is included in each post request submitted to the server. In HTML forms, the token can be included as an additional hidden input value. So when the submit button is clicked, this value, together with other values, is submitted to the server. The server then verifies the token's value, making sure that requests with missing or incorrect token values are rejected by the server. Now, if you think about it, what it does is that it makes each request unique and unpredictable by the attacker, because the attacker does not know what token value has been assigned to the victim's browser session. For sure, the attacker can find out the token value that has been assigned to the attacker's browser session. But the attacker cannot use that value in the attack, as the server will expect a different value for requests that come from the victim's browser session. The security requirement here is that these token values should be generated in a similar manner as the session IDs for authentication cookies are generated. This should then ensure their unpredictability. Another note is that CSRF tokens should not be stored in cookies. There are some applications that issue a cookie with a CSRF token in it, and then when receiving a post request, check that the token value in the request matches the token value received in the cookie. But these implementations are quite fragile because if the attacker can somehow execute cookie injection or overriding attack, then the CSRF protection of the website can be bypassed. So it is more secure to store the reference value of the token on the server side bound to the user's session cookie. But anyhow, this is how CSRF tokens work. And to repeat once more, the use of CSRF tokens is the most reliable CSRF defense mechanism that we have today. Some applications use refer-based validation to prevent CSRF attacks. Normally, this is done by verifying that the HTTP request's refer header contains the website's own domain. If it does, then we can conclude that the request comes from the same site and therefore could not have been forged. Here is code in PHP. So in case of request method equals post, we parse out the hostname from the refer header and compare it to the server's name. If they do not match, then we consider it to be a cross-site request and the execution stops. Basically, we can add this code at the top of our codebase and it will protect against CSRF all post requests received by our website. Pretty neat, right? Now, the problem is that refer header might not be always present in a request. There are some exceptions. A refer header might be omitted when opening a URL from a non-URL context. For example, writing a URL in the address bar, clicking on a bookmark, clicking on a URL in some other application than a browser, and similar situations. This, however, in practice would concern only GET requests. A somewhat bigger problem is that refer header might be omitted when using browser privacy extensions. There are some very aggressive privacy settings where the refer header is removed from all the requests made by the browser. Therefore, we cannot assume that requests without refer header are same-site requests. Another reason is because an attacker can force the victim's browser to omit the refer header when making the request that is part of a CSRF attack. This can be done by specifying rel noRefer for individual links, or can be enforced for the entire web page by using the HTML meta element or by returning the refer policy header. Therefore, to be on the safe side, post requests without refer header must be rejected by the server. And this now becomes a business decision whether to exclude users who use aggressive privacy settings in their browsers. Due to that, this is a very simple but also a rather fragile CSRF defense mechanism. The fetch metadata request headers is a quite new browser security feature which informs the server about the context in which an HTTP request is made. The idea here is similar to the refer header validation, but this is a much more reliable method for blocking cross-site requests. Let's look at an example. Let's say some website embeds an image from crosssite.com. To fetch this image, the browser will make an HTTP request to crosssite.com, but in addition to the usual headers, the browser will also include these three segfetch metadata request headers, which provide more detailed information about what happened on the browser side. The test header tells that the request originated from an image element. The mode header tells that this was a simple no-course request, and the site header tells that the request originated from another website. Let's take a look at what values these headers may contain. The segfetch test header indicates the destination of the requested resource, meaning where and how the requested data will be used. The destination will contain the value empty if it is a request made using, for example, the fetch API. The document value will be used if this is a result of a user-initiated top-level navigation, for instance, when a user clicks on a link. And then there is a list of HTML elements specifying which element is loading the resource. And actually, there are quite a few HTML elements that can load a resource. The segfetch mode header indicates the mode of the request. Navigation means that the request is initiated by navigation between HTML documents. No course, that it is a simple no course request. Course, that it is a course protocol request. And same origin means that it is a same origin request. The segfetch site header indicates whether the request comes from same origin, same site, cross-site, or is a user-initiated request, meaning that the user entered the URL into the address bar or clicked on a bookmark, as there will be no origin in such cases. There is actually one more header, segfetch user, which will be present only in case a navigation request originated due to a user interaction, such as by clicking a link. Otherwise, this header will be absent. So what these headers provide us in practice is that unauthorized cross-origin requests can now be blocked by the server without processing them. So by using this method, the server can easily block cross-origin post requests to prevent any post-based CSRF attack. But we can go even further and forbid other websites from embedding our resources, which would also then mitigate timing and embedding-based access leaks, which is quite linked, right? Now the problem here is that this security feature is not supported by legacy browsers. Apple's Safari browser was the last one to add support for it in April 2023. Therefore, unfortunately, we will have to wait for a couple of more years until legacy browsers are upgraded. Or another option is that we could simply block requests from legacy browsers, which actually might be a good idea if we are running a security-critical website and we don't want to serve users on outdated and potentially compromised platforms. As another defense mechanism, there is the SameSite attribute of cookies. This attribute controls whether a cookie is sent with cross-site requests, and therefore it can help to prevent cross-site request forgery attacks, because, as we already discussed, CSRF and access leaks are possible mainly because browsers include session cookie in cross-origin requests. So we can use this cookie attribute to change that. There are three possible values that this attribute may contain. SameSite equals none means that the cookie will be sent on all cross-site requests, which basically means that this option provides no protection against CSRF. And this used to be the default behavior of cookies before this cookie attribute was introduced in web standards. Now, SameSite equals slacks, however, is very useful as it provides protection against post-based CSRF attacks, meaning that the cookie will not be included in any of the cross-site post requests, which is already good, considering that post requests are the only requests that we should protect against CSRF. But interestingly, it goes even further, as it also provides protection against some GET-based CSRF attacks. In particular, the cookie will be omitted in all cross-site requests that embed a sub-resource, including all cross-site requests that use the fetch method. So in all these cross-site requests, the cookie will not be sent. However, if a user, for example, clicks on a link, submits a form that uses GET method, or the user's browser is redirected to a URL, then the cookie will be included in such a cross-site request. So, as long as the request involves a top-level navigation, the browser will include the cookie. Therefore, as you see, this does not really prevent exploitation of a GET-based CSRF. What it does, however, is that it makes exploitation of a GET-based CSRF less stealthy, as the user browser will be navigated to the target website. And more importantly, it prevents timing and embedding-based access leaks, which we discussed in the previous lecture. So you see, actually, there is a very good reason why to omit cookies in cross-site GET requests that do not result in a top-level navigation to the cross-site website. Now, SameSite equals strict is the most strict setting, as it provides protection against both GET and post-based CSRF, as the cookie will not be included in any cross-site requests. But here the question is whether this is not already too restrictive, because what the strict setting means is that basically The only case when the cookie will be sent is when a user types in the URL in the address bar and presses enter. So if we would try to access a website by clicking on a link present in some other website, the browser would open the website, but the website would behave as we have logged out. The subsequent clicks inside the website will send the cookie, but that initial landing on the website may be rather confusing for the user. So this behavior might be acceptable if we consider, let's say, some online banking website, but definitely not for social networking sites such as YouTube or Facebook. Therefore, the lax setting might be the optimal choice for most of the use cases. Note that setting SameSite cookies in requests from which they are omitted will be rejected by the browser. This is to prevent such cross-site requests from overwriting the existing SameSite cookies. The SameSite cookies are supported by all major browsers since 2018, so there should not be in use too many legacy browsers that do not enforce this. To summarize, SameSite equals lax or strict should be set for authentication cookies. This is the best practice regardless of other anti-CSRF measures that might be applied by the website. And it is important to set this value, because if this value is not set, then while Chromium-based browsers will default to lax, Firefox and Safari will default to none, failing to enforce any protection provided by SameSite cookies. Now, the security issue with these SameSite cookies is that the SameSite is weaker than SameOrigin. The SameSite here is not defined as a hostname, but rather as a root domain name including all its subdomains. And therefore, cross-site request forgery attacks and access leak attacks from subdomains are still possible. This means that if any website belonging to the same root domain is compromised, or even if it just has an XSS vulnerability, then this can be used to execute CSRF attacks bypassing these SameSite cookie restrictions. And this is the biggest issue why SameSite cookies do not work as a complete solution against CSRF, unfortunately. Therefore, this SameSite attribute should be applied just as an additional countermeasure against CSRF. Now, the cookies partitioned attribute provides an alternative to SameSite cookies. Here the idea is that instead of omitting cookies from cross-site contexts, the cookies are partitioned or isolated based on the top-level site that performs the cross-site request. Here's how it works. We can specify the partitioned attribute, which will instruct the browser that the cookie should be stored using a partition storage. Which means that embedded resources under each top-level site are given a unique cookie storage space or a unique cookie jar. So when the target site a.com is accessed as a top-level site, it will have access to unpartitioned cookies. But when its resources are used in other top-level sites, then under each top-level site, it will have a different cookie storage. This enables use cases where a site embedded in an iframe can have access to cookies and still properly function, but the user browser session is isolated from other sessions where the site is accessed in other website contexts. Pretty neat. We will discuss this more in a future lecture where we will study the cross-site tracking issue. Now, as you see, this type of cookie isolation should provide some CSRF protection. And indeed, it provides protection against some GET and POST-based CSRF, but only against some. The cookie jar is partitioned when embedding cross-origin resources and making requests using fetch. However, the cookie jar is unpartitioned for all cross-site requests that involve top-level navigation to the target site, including when making a cross-site POST request using an HTML form submission. Therefore, this does not provide any CSRF protection in practice. This only prevents stealthy CSRF attacks where the user browser is not navigated to the target website. So this makes the cookie partitioning mechanism pretty useless as an anti-CSRF measure. Note that this partitioned attribute is supported by Chromium-based browsers only. However, where it gets interesting is that this kind of cookie partitioning is enforced by Firefox and Safari for all non-SameSite cookies and all SameSite equals none cookies. Now, it may seem that Firefox and Safari are doing a great job here by enforcing such partitioning for all non-SameSite cookies. This indeed seems better than including unpartitioned cookies in all cross-site requests. However, the problem is that in Firefox and Safari, this type of partitioning can be easily bypassed. To achieve the partitioning bypass for 30 days, it is enough if an attacker's website opens a pop-up to the target website. In such a case, the unpartitioned storage access will be automatically granted to the attacker's website, and the attacker's website will be able to perform cross-site requests using the same unpartitioned cookies that are used when the user accesses the target website directly. The reason why such a bypass is enabled by browsers is to support legitimate use cases where a third-party website would need to perform cross-site requests using unpartitioned cookies. So here it is important to stress that the aim of this partitioning measure is not to prevent CSRF, but rather to improve privacy by preventing trackers that are embedded in various websites from performing stealthy cross-site tracking of website visitors. But again, we will discuss the tracking issue in a future lecture. And by the way, Safari in the latest version does not apply partitioning, but simply omits non-SameSite cookies in these cross-site requests. Anyhow, the conclusion here is that this is not an anti-CSRF measure, and therefore, when possible, the SameSite attribute should be used instead. The final measure, which is more of a side effect rather than a deliberate CSRF protection measure, is for a web application to use non-simple fetch API requests when performing state-changing activities. To remind you, non-simple requests are those that use a non-standard HTTP method or set non-standard headers. Here is an example of such a request. So if we consider our logout use case, then after a user clicks on the logout button, this HTTP request with a non-standard header will be submitted to the server. This will work as an anti-CSRF measure because non-simple cross-origin requests require coarse authorization. So if a cross-origin website will try to make such a request, the browser will send a pre-flight request using the HTTP head method to check whether the target origin authorizes such a non-simple request, and the attack will fail. A common example of such a side effect is when a website's frontend uses JSON-encoded POST requests to communicate with the backend. The CSRF attack will not work because we cannot use such a content type header in cross-origin requests without the cross-origin resource sharing authorization. Of course, this measure works only if the header is checked by the website's backend, meaning that the website refuses to process requests where this header is absent. And obviously, the use of this measure requires the JavaScript support enabled. The website cannot make such requests without using JavaScript. But this should not be an issue in practice, as browsing today presumes JavaScript enabled. The reason why this method is not recommended as a universal anti-CSRF measure is because it mitigates CSRF only for such JavaScript-initiated requests. However, this might be a very useful anti-CSRF measure for non-browser HTTP APIs. For instance, if we are providing a public HTTP-based API which is not supposed to accept requests from browsers, then we can block browser-initiated requests by simply requiring requests sent to our API server to contain a non-standard HTTP header, which cannot be set by a cross-origin website. Note that it may be a good idea to personalize the name of the custom header used, for example, by introducing in it the name of the website. This will guarantee that there is no other application that by accident uses the same header name, which in some cases may prevent some API endpoint confusion attacks. But to summarize, these were the 5 anti-CSRF measures that can be used in practice. Which one to use in your application, that's a decision that you have to make. Anyhow, with this we end the lecture. Good luck with the homework.